Okay, I'm back on YouTube again for what it's worth. Gravitational lensing and Einstein rings, again, such as the image you're seeing there on the screen. When light travelling through the universe passes a massive object like a galaxy, its path is bent because, according to Albert Einstein's theory of general relativity, the gravity of the massive object distorts space and time around itself. As a result, sometimes when we look at distant galaxies, we can see distorted images of other galaxies behind it. And if things line up perfectly, the light from the background galaxy will be smeared out into a circle around the closer galaxy. The distortion of light is called gravitational lensing, and the circles it can create are called Einstein rings. By studying how the rings or other lensed images are distorted, astronomers can learn about the properties of dark matter halo surrounding the closer galaxy. So, axions versus WIMPs, and that's exactly what Amarath and his team have done in their new study. They looked at several systems where multiple copies of the same background object were visible around the foreground lensing galaxy, with special focus on one called HS 0810 plus 2554. Using detailed modelling, they worked out how the images would be distorted if dark matter were made of WIMPs versus how they would if dark matter were made of axions. The WIMP model didn't look much like the real thing, but the axion model accurately reproduced all the features of the system. The result suggests axions are more probable candidate for dark matter, and their ability to explain lensing anomalies and other astrophysical observations has scientists buzzing with excitement. So, the new research builds on previous studies that have also pointed towards axions as they more likely form of dark matter. For example, one study looked at the effects of axion dark matter on cosmic microwave background, while another examined the behaviour of dark matter in dwarf galaxies. Although this research won't yet end the scientific debate over the nature of dark matter, it does open new venues for testing and experiment. For example, future gravitational lensing observations could be used to probe the wave-like nature of axions and potentially measure their mass. A better understanding of dark matter will have implications for what we know about particle physics and the early universe. It could also help us to understand better how galaxies form and change over time. Interesting stuff, that is. And we're still streaming. YouTube is active again, still. You're tuned to ASV Radio, VK3 Echo Kilo Hotel. Okay, just looking at the Discord channel. We've also got another one there. G'day, Wayne. Just reading the email there. Thanks, Wayne. Okay, this next one. Hubble spots runaway black hole, leaving behind a trail of new stars. If confirmed, the first of its kind find would serve as convincing observational evidence that supermassive black holes can indeed be ejected from their parent galaxy. Astronomers think they have discovered a black hole some 20 million times the mass of the Sun, speeding away from a core of a distant galaxy. And as the supermassive black hole barrels through intergalactic space, it's compressing the scant gas and dust available out there, leaving behind a thin line of newly formed stars that's some 200,000 light years long. Now, there's an illustration of this, so I'll just bring that up. Where's my illustration? It should be there, it should be there, it should be there. I can't see it though. Why isn't it? Oh, here we go. So I didn't part that image through. Well, wouldn't it bother you? I can easily do this. It only takes a second to copy that image out and put it there, and then bring it into vMix. So just hold on to your linen while I just do this, because I thought I did it, but I didn't. And now there it is there, and import it into vMix, and there we go. And now we can bring up this image, which is just there, and cut across. So there it is. That's the artist's impression, at least. But they do have some photographic evidence here, which I'll bring up in a tick. This illustration shows the suspected runaway black hole and the thin trail of new stars linking it back to the apparent galaxy it was apparently tossed out of. So we can now bring up more of an image that's actually what they're looking at. There it is, this one here. This is more accurately the real thing. So what you're looking at now, for those that are still watching the visions, and YouTube is still streaming, the strange linear feature was the first identified in this archival photo captured by the Hubble Space Telescope. Follow-up observations have shown the feature is actually a chain of young blue stars some 200,000 light years long. So that's what you're seeing on the screen right now. That chain of young blue stars, 200,000 light years long. Amazing stuff. Getting back to the article. We think we're seeing a wake behind the black hole where the gas cools and is able to form stars. What we're seeing is the aftermath, like the wake behind a ship. We're seeing the wake behind a black hole. Despite being relatively thin, the black hole's stellar wake is packed with plenty of hot blue stars, making it nearly half as bright as the apparent galaxy it traces back to. Based on the available evidence, the researchers think this black hole was likely ejected during a complex dance between three supermassive black holes that were involved in a pair of galaxy mergers. If confirmed, this would be the first observational evidence showing that supermassive black holes can be ejected from their parent galaxies. Yeah, I'll leave it at that. Actually, there's a bit more to that article, but I shan't carry on. But suffice to say that the rest of it can be read from astronomy.com under the news tab. Hubble spots runaway black hole leaving behind a trail of new stars, which is really quite fascinating. Okay, there's another camera running there that I've just switched in. Unfortunately, this one likes to flicker, so put up with the flickering for a bit. YouTube is still running, from what I can see. Oh, by the way, we, as you all know, a few days ago we had some very interesting auroral activity, and this image captured by Eddie Pang, a member of the ASV, while up at Heathcote, and this was last, I think, Monday morning, 5 o'clock in the morning. This amazing image of the Aurora photograph from Heathcote, the dark sky site. In the foreground is the 8.5 metre radio telescope up at Heathcote, so it's beautifully silhouetted against the Aurora that was photographed by Eddie. Good on you, Eddie. I'm not sure if you listened to the casts, but good on you. Excellent photographer. He takes some real good pictures of some deep sky objects too. There's another picture here too of that's the Aurora that occurred early last week. This one is by Mr. Dalker. I'm not sure of your first name, but it's by another astronomer. Just thought I'd throw that in as a bit of a break. Okay, next article is to do with astronomers are using artificial intelligence to discover fledgling planets. Artificial intelligence can help astronomers more quickly and efficiently discover young exoplanets hidden in protoplanetary disks and even catch worlds that human researchers miss. April 27. And there's an image here that I can bring up as well. So what we're looking at there is the young star HL Tau, TAU. The young star HL Tau sports a massive protoplanetary disk of gas and dust. Forming planets often carve out gaps in these disks, giving away their presence. So that essentially what you're seeing there, and I'll just check, yes, my YouTube is still running. What you're seeing there, to those watching the visual side of this, that effectively is how our solar system began. In that, if we could go back many millions of years ago, billions, that is a protoplanetary disk, and those gaps within the disk are potentially being caused by planets being formed. So there's an early evidence of how our solar system formed so long ago. The number of known exoplanets has exploded in recent years, with more than 5,000 worlds beyond our solar system now known. But there is a catch. The worlds we've found are typically those easiest to detect. It's only as techniques and technology improve that astronomers are able to discover planets that are harder to see. Now, the field has made another step forward with two recent papers, one published 23rd December and the other on April 21, both in the Astrophysical Journal. In them, researchers show how they've used machine learning to spot the subtle signs of forming planets within the thick disks of dust that surround young stars. Such a tool could improve how quickly and efficiently astronomers can find young planets, and it comes right at a time when new and upcoming telescopes are poised to provide an avalanche of data on exoplanets in the Milky Way. So what's in a protoplanetary disk, you might ask? When a star is born, it lies ensconced within a thick disk of dust and gas. It is this disk, called a protoplanetary disk, that provides the material from which planets form over millions of years. Astronomers find and study these often massive and far-reaching disks using infrared and radio light. But discovering any young planets embedded within such disks is difficult. The dense material obscures our view, forcing astronomers to infer the presence of planets through their effects on the disk itself. In these cases, astronomers indirectly find the still-forming worlds by looking at how they affect their surroundings, changing the way nearby material orbits and eventually carves out gaps in the disk. It is those gaps that serve as beacons, telling astronomers, "Look here." Traditionally, such searches have been carried out manually, explained lead author and doctoral student Jason Terry of the University of Georgia in Athens in a press release. Researchers study numerous images looking for any telltale signs of forming planets, then run possible finds through multiple simulations to determine whether they've spotted something real or not. But astronomers, as the saying goes, are only human. Manual searches take time, and humans can miss difficult to find clues, such as when the metathorical waves made by burgeoning planet are tiny compared to the motions of the rest of the disk. That's where AI comes in. With its ability to quickly analyse large amounts of data and pick up on subtle hints that humans might miss, this tool has now proven its valuable time and money-saving resource in the hunt for new worlds, including those we might otherwise overlook. The team's studies focused on training a machine learning algorithm to find young planets embedded within disks using completely synthetic data. Once the AI was trained up, however, they turned it loose on real observations to determine whether the algorithm could identify known exoplanets and possibly find new ones. This has never been done before in the field and paves the way for a deluge of discoveries as James Webb Telescope data rolls in. The result was a resounding success. Not only did the AI accurately point to the places in disks where planets are now known to be forming, it also flagged the disk around the star HD 142666, where astronomers previously hadn't identified any planets. When the team followed up by running simulations on the potential find, we found that a planet could recreate the observation. Terry said, in a second release on the discovery, the team concluded that HD 142666 hosts a planet 5 times the mass of Jupiter, orbiting about 75 times farther than the Earth sits from the Sun. We knew from our previous work that we could use machine learning to find known forming exoplanets, said Hall. Now, we know for sure that we can use it to make brand new discoveries. So, according to study authors, finding actively forming planets is an area where AI has rarely been applied, but it is also an area that stands to benefit greatly from the tool's use, particularly because of the delicate and difficult nature of the work. In a sense, we've sort of just made a better person, said Terry. This method is 1, really fast, and 2, it accurately gets planets that humans would miss. He acknowledged that scientists are often skeptical of adopting artificial intelligence, but he also emphasized that the algorithm is clearly up to the task. In this case, we have very concrete results that demonstrate the power of this method, he said. Racking up additional planets is about more than just reaching increasing impressive numbers. The more planets astronomers find, the more that they